Hope more people will connect in a few minutes, but maybe not, I don't know.
Okay, do you think would you like to wait or should we begin?
It's up to you.
Let's give it 2 minutes and then it will be a nice round number.
One issue is that your handwriting is not full screen, so I think how to make it.
Yeah, I'm not very smart about it. Can you pin it? Or is there a sort of pinning?
I think it should be possible. But if I make a co-organizer, will that help?
I see that I'm the co-host. Bergfalk phone is the co-host. I don't know if that helps.
Yeah, but it doesn't help.
If I pin it, then it becomes big. I think if our listeners pin it, if the viewers and listeners, so in the corner there's something, there's 3 dots for me. If you go to the corner of the screen, and then if you hit pin, this seems to prioritize this window.
Yeah, it worked for me. So in Russian, it's called закрепить pin.
Okay, so people should try this. Okay. Then maybe we should begin. Okay. So let me begin, of course, by thanking the organizer, Sergey, for the invitation, and thanks to everyone for coming. And I'll just say a few words about who I am mathematically and how this came about. So in my heart, I think most fundamentally, I'm a set theorist. What this means is that I care very much. I think very much about things like omega-1, omega-2, infinitary combinatorics. And I'm probably most fundamentally interested in these things, but something that's been happening that's very exciting to me and a few others in recent years is that there's been a very big stimulus coming from questions in homology theory towards how we approach these sorts of objects, and so in learning more about particular homology theories, things like strong homology, I began to see Sergey's name, some of his publications on Archive, and it was clear that he had digested these things that I was trying to digest much more deeply than I had. And I wrote to him with compliments, and he invited me to this meeting, and that's how this came about. So I'll say a bit about what I plan to discuss today. I'll be not assuming a lot of background either in set theory or in homology theory. When I get into the homology part, I'm going to feel a little weird because I think probably some people here know a lot more about it than I do. In any case, I encourage people to speak up and interrupt if they have questions at any point. Please let me know if I'm going too slow or too fast. And so I'll just say I understand that we have 2 hours. And if we get done sooner, that's probably fine. And if it goes beyond that, then it would have to be really, really interesting for it to go beyond that, I think. And so, again, I'm very flexible and I encourage feedback and want to hear from you throughout. So let me just say the plan for today, I think, is number 1. That looks a little small. So number 1, I want to just give some background on set theory. really what I would like here is I don't want to, I don't want to get too deep in any technical details, but I want to facilitate communication. I'm sorry for the blur. I want to facilitate communication between set theorists and more general mathematicians, because set theorists sometimes they'll say, let's invoke an assumption like the continuum hypothesis, or the open coloring axiom, or a large cardinal like a weakly compact cardinal, something like this. And these are very efficient ways of communicating for set theorists, and I would like them to be ways of communicating with other mathematicians as well. So I just want to sort of say a bit about what people should hear when they hear things like that. And because they come in to these problems arising in homology theory. And so I'll try and efficiently talk about these things in homology theory. That'll be number 2. And then I want to just give 2 arguments that I'm going to call classical. They're from the 80s, 2 arguments in this area that give the flavor of sort of the interaction between set theory and homology theory that's really been growing in the past few years. So these are older, but I think they give you a taste of the kinds of interactions that interest me. And then in number 5, time permitting, I'll just give an overview of more recent results. And if we get to 6, I doubt we'll get to 6, but if we get to 6, 6 would be why I really care about this. So there are nice interactions here, but there's sort of deeper sort of meta reasons, underlying reasons that I'm excited about this, that I think you can only begin to perceive at 5. So we'll see. In any case, in 1 and 2, this is going to be more intuitive, more conceptual. It's going to involve more words. Some of these I have already written out. In 3 and 4, this will be more quote unquote mathematical. So we'll actually do the arguments. We'll actually go through the reasoning. But in 1 and 2, there will be some hand waving. And of course, this is a matter of taste. Let me know if I'm waving my hands too much or too little. So, and also, I don't know really what to assume of anyone's background in set theory. So if I say ordinals and that makes people uncomfortable, then we can stop and we can talk more about what ordinals are. Okay, so some of these these are my slides, so to speak. So some of these I've already sort of written up. Can everyone see these clearly? The lettering's a little smaller. So this is number 1, a brief overview of the relevant set theory. In particular, how I'd encourage more general mathematicians to hear hypotheses like CH for the continuum hypothesis, PFA for what's called the proper forcing axiom, and there exists a weakly compact cardinal. So these are sort of the 3 of the more prominent assumptions that that do some of the work that I'm talking about. Okay, and okay, here again the wording is smaller. I hope people can see this, but I'll read it. So I'll speak of models of set theory. I can't see screens and I can't see hands, but someone should speak up and say, if I speak of a model of a theory, is this a comfortable idea for everyone? So you have a theory in a language. The language of set theory has one relation, that's the membership relation. And then we can speak of models of it. So a model of set theory or a universe, usually it's depicted by a V. Sometimes it's depicted by an M. V is just a collection of elements. And then between any two of these elements, we may or may not have the membership relation. X is an element or Y, something like this. That's it. So you have one binary relation on a collection. I might say set, but this could be larger than the set. It could be a class. This is a model of set theory. Much as we have the axioms for groups, you have an operation with association, with inverse, things like this. A model of those axioms is a group. A model of set theory is something like this. Now, what's different between the group theory and set theory examples are when we talk about these axioms, the Zfc axioms, unlike when we talk about the axioms for groups, these axioms carry some extra charge, philosophical charge. In other words, these axioms are thought of as encompassing, with unusual transparency, the most fundamental principles of mathematical practice and reasoning. So when we talk about a model of set theory, we're talking about a formalization of the practice of mathematics itself. This is one way of thinking about it, okay? At the same time, these axioms are construction rules for building sets. And so, again, I'm assuming familiarity with the Zfc axioms, but I'll just to remind ourselves what they look like. So this is from, one of the classic set theory texts. It's by Kenneth Koonin, who recently passed away. So these are, for the most part, utterly uncontroversial propositions. There exists a set. Two sets are the same if they have the same elements. If you have an X and a Y, there's a set containing X and Y, things like this. These are the Zfc axioms. So Zfc, as we know, Z stands for Zermelo, F stands for Frenkel, and C stands for choice, the axiom of choice. And so these are at once, so for example, there was the pairing axiom that I mentioned. If you have a set X, you have a set Y, then you have a set X comma Y. So these are construction rules for building sets, but at the same time, they do this extra work. Now, what is surprising and perhaps frustrating, but in any case interesting, is the fact that these ZFC principles settle many, but not all, of our favorite mathematical questions. Okay, in other words, there are, I've lost my pen. In other words, there are a multiplicity of models of set theory amongst which the answers to some of these questions may vary. Now, the most famous of these examples is the continuum hypothesis. So, okay, this is sometimes abbreviated CH. And we might write it as 2 to the aleph naught equals aleph 1. Equivalently, it's just saying the size of the collection of real numbers is aleph 1. Equivalently, it's saying every subset of the reals is either countable, and for me, countable means possibly infinite, possibly finite, but countable, or of size continuum. Okay. Okay, and someone should give me a thumbs up or something to indicate that when I say aleph 1, it's clear what I'm talking about. Because we can take a moment to talk about ordinals and cardinals.
I hope it is clear.
Okay.
If not, please say.
Okay. So with respect to the continuum hypothesis, we have the following theorem. So this is 1936, and this is Girdle. Okay, if the Zf axioms are consistent, then so are the axioms Zfc plus Ch. These are modeled by what's called Girdles Constructable universe, which is usually abbreviated L. There's an idea here which we can crudely represent pictorially. One thing set theorists don't have a lot of is pictures. I mean, I think this is a geometric topology seminar. This is a book about set theory. It has 2 pictures. The pictures are terrible. They're laughably crude. There's only one picture. It's this. But the idea is that the universe of set theory is built up from the bottom up. You begin with the empty set. You take the power set of the empty set. And then you take the power set of what you have then, and you continue in this direction. Every set arises at a certain point. And so every set has an ordinal index or a rank. It has a first place that arises in the universe. So the universe is built from the bottom up. And this is a picture that is in most set theorists' mind when you say something like V. But of course, what's complicated and what I'm talking about is that this language, universe, and this picture suggests that there's just one V. But again, our experience of independence and of theorems like this is that actually there are many universes. Girdle's universe, when we talk of a constructible universe, this is in fact an inner model or a sub-universe of any universe of set theory. So if you take any standard universe of set theory, a picture like that, within it, you have this, you have L. So again, all I'm trying to provide at the moment is just some intuitions. As you build up V, Girdle's idea was that if you just have the Zermelo-Fraenkel axioms, not even choice, as you build up this universe V, at each stage, when you start to get up into infinite levels, omega plus 1, and you're taking power sets, you're taking a lot of sets and throwing them into your universe. Girdle's idea was to take only the quote unquote definable ones, the ones that we could speak about in a first order formula in the language of set theory. So what Girdle's idea was just to build up this language, adding only what we can't avoid adding. And he showed that this universe that he built up, in fact, is a model of the axiom of choice, and in fact is a model of the continuum hypothesis. So he showed that the continuum hypothesis is consistent with these axioms. And this is, so what I would stress here is that anytime anyone hears about the constructible universe L, or hears the axiom V equals L, what they're hearing is sort of a movement in. They're hearing about a narrow universe. In contrast, with respect to the continuum hypothesis, we have a theorem in the other direction by Cohen, if the ZF axioms are consistent, and so is ZF plus not AC. This won't be our focus, but it's significant enough. It's worth recording. And so is ZFC plus not CH. And this, together with Girdles' result, showed that ZFC does not determine the value of the continuum, that the value of the continuum is independent. These theories are modeled by forcing extensions, also known as generic extensions. And what I would stress here is that this is a movement out. In other words, if you have V, what's happening with the forcing extension is that you're widening your universe. And the usual analogy that's given here is something like a field extension. And you can even see this at the level of the notation. Something has been added to V, which V needs to expand to accommodate, in the sense that it, with that object alone, would no longer be a model of set theory. But if you add some more things in, then it's again a model of set theory, but a larger one, much like field extension. So here we have a movement out. This G, just to give people an idea, is a generic object with respect to some partial order P. And for Cohen, P was the set 0, 1, less than omega, of finite binary sequences. Ordered by end extension. So there's a picture here. And the picture is something like, okay, empty set 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, etc. So this is a partial order by end extension. And forcing is always done with respect to a partial order. So you begin with your universe, and you want to, and what's amazing about forcing is that you have some property that you target. And the way that you target it is by devising a very particular partial order to hit this assertion that you want to prove, whose value you want to change. And so that partial order is often collection of approximations to the thing that you want add. So in this case, these are a collection of approximations to an infinite sequence of zeros and ones. Now, to a set theorist, we think of this as a real, as an element of the Cantor set, as an element 2 to the omega. And this generic object is generic or typical, too typical. In other words, it's too representative of the model that it lives in, or of the model that it's emerging from, to remain in that model. There's a way of making all this formal, which is that it hits every dense set. A dense set in a partial order is somebody such that below any point, there's an element of the dense set. So a generic object is in fact one which hits every dense set in your base model, in your ground model, V. And Cohen's insight is that without loss of generality, using some sort of logic hocus pocus, you can always arrange that these things exist. And so if you have a model of some things, if you have a model of ZF or ZFC, then you can set up your partial order, and then without loss of generality, your model is one with respect to which there exists a generic, and you can pass to this larger model. And so this was the first one. And in fact, sometimes you can have different partial orders that are quote unquote forcing equivalent, meaning that they give you the same extension. They do the same thing. So this is a very sort of elementary and combinatorial description of a partial order which could also, of a forcing, which could also be given if you just take the co-Meeker's subsets of the real line. That's a partial order also. And you could force with respect to the co-Meeker's subsets of the real line, and you would get, again, a real number, which was not in your original ground model. This is Cohen's insight. You can add real numbers and you can keep doing this. Okay, so that's the idea here. What I want to emphasize, all I really want anyone to take from this page is that different partial orders produce different extensions of the base universe V with different properties. And so you could start with your V, here's V, and then you have some partial order which will take you to V of G, and then you could have another partial order, and then you get a generic with respect to that partial order, and then you get your V of G of H, and so on. Okay. And a forcing axiom describes a closure point or a limit point of this process of widening and widening and widening your universe. It should be thought of as saying that one has done all the forcings of a certain sort, and as saying that one's universe is unlike L. Unlike L in the sense that it's the result of a lot of widening, whereas with L, the motion is in the opposite direction. Okay, and this brings us to the most important contrasting hypothesis with L, which is the proper forcing axiom. Now, I'm not going to say what the proper forcing axiom is. What I am going to give you in hopefully about 30 minutes is a consequence of the proper forcing axiom that anyone can use. I mean, that I think is, you don't need any knowledge of forcing to use. That's called the open coloring axiom. And so again, these are two main things that I want to communicate. These are two hypotheses you might see in set theoretic context. One is V equals L, saying that the universe is L. One is PFA. When you hear this, you should hear that this is a narrow universe. And you should hear that this is, in some sense, a wide universe. You should also, when you hear V equals L, you should know that 2 to the aleph naught equals Aleph 1. The continuum hypothesis is true in Girdles' universe. In PFA, as it happens, 2 to the Aleph naught equals Aleph 2. And this is a universe which, again, is due to Gödel in the 30s, but people only really began to understand it in the late 60s and in the 70s. PFA is really an artifact of the late 70s and early 80s. And a lot of them, some of the math that we'll be talking about today played a role in our understanding of PFA, some of this math which was coming from homology. And I think it's also worth, okay, so there are also some with any of these things, there are combinatorial principles. So these are sort of large hypotheses, but you can have sort of finer hypotheses. Sometimes these are, there's a diamond, there's a square, things like this, and you can sort of break off. And then with PFA, you have nice combinatorial principles like OCA, and this is one that we're going to focus on today. This is called the open coloring axiom. There's no reference to forcing, you just talk about colorings. And it has applications in analysis, things like this. And then the last, this is really an intuition, but I think it's a valuable one. I think non-set theorists, when they think of CH, they think of that as the nice hypothesis. Generally, set theorists, many of them look at CH as sort of the bad hypothesis. This is where a lot of your monsters live. In V equals L, this is where you get a lot of pathological objects. A forcing axiom says sort of, okay, you have, you have some things that are overlapped that fit together in maybe a funny way, then you forced enough that they actually, you sort of homogenize things. This is a nice world. This is a nice universe. And I'm going to give you an example in just a moment. But this is a world of more pathological objects, partly because the continuum is small. You can do a lot of inductions just going up to the continuum. You can diagonalize against things. You can build things like Luzin sets and crazy things. Okay, so with this behind us, I'm going to talk about what's going to be our main example today. So there's a main combinatorial question about coherence and non-triviality, and we're going to see that it behaves differently under these two assumptions. So our main example. I see again, please let me know if the image is unclear. It seems to be coming in and out. Okay, so the setting for our main example is just omega squared, or the natural numbers times the natural numbers. And what we're going to be looking at, so here's an F going from omega to omega. And this space here, this I'm going to call I sub F, or let's say I parentheses F. So I parentheses F from now on is going to be Ij such that J is less than or equal to F of I.
This is not visible very well.
Yeah. I wonder if there's an issue of light or other things giving it other things to focus on. No, it's not so readable. That's not better yet, is it?
Not so good. Maybe if you just wave your hand in front of the camera.
strange. I can write larger.
Yeah, it's not bad. If you write a little bit larger, it would be visible.
And we can bring the page closer. Would this be better? It's strange.
Yeah, thank you. Better now.
Okay. So what I'm going to be interested in, what we're, I hope, going to be interested in, family of functions phi sub f I of f to z for f is coherent if phi sub f restricted to I of f g equals star phi sub g restricted to I sub g. For all f g. Okay. I can see that the image is still not so good, and I can't explain that. One possibility could be that I log out and log back in with the phone. But maybe I'll finish this page and then we can try that. Sergey, does that sound all right? Or should we?
Yeah. So you're taking the minimum of pointwise minimum of f and g, right?
Yeah. So yeah, let me say what this is. So what I have in mind is I have f, which is a function from omega to omega. I have another function g, which is a function from omega to omega. And I'm looking, when I write I of f, I'm looking at the space below f. And I have a function from, so you can maybe think of this as having another axis, which is the integers. I have a function from the space below f, from the below the graph of f to the integers. And I also have one from below the graph of g to the integers. And this collection of functions is coherent if in this space below them both, in the domain that they share, they only disagree finitely often. So this is disagreement.
You're right. Equality with star. Is that star?
Yeah, so equality with star means mod finite.
Okay. Thank you.
And I will probably get, later if we get to it, I might get lazy, notationally lazy, and omit the restrictions. So I might write phi sub f equals star phi sub g to mean this. instead of writing this over and over again. Okay, so a family of functions. So we have a family of functions which I think of as they're like this, they're lying over each other, and then they disagree finitely often. That's a coherent family of functions. This is a local property. The natural question is whether it globalizes. So let's say phi phi is trivial if there exists a phi from omega squared to z such that phi restricted to I of f equals star phi sub f for all f from omega to omega. Okay, so it's definitely, it's not difficult to see that if phi is trivial, then it's coherent. The question is the implication in the other direction. If you're coherent, are you trivial? And this is an interesting question. This is the kind of question that a certain species of set theorist loves to think about. And it's a question that's actually very good at sort of probing what kind of universe you're in. As we'll see, if V equals L, then there are non-trivial coherent families of functions. On the other hand, under the proper forcing axiom, every coherent family is trivial. So again, this sort of accords with some of what I was alleging about these two universes. I said that V equals L has more sort of pathological objects, maybe more messy objects. Here's a thing where everything fits together nicely locally. That's a coherent family, but there's no global way to make it all work together, right? So that happens in V equals L, but it doesn't happen under PFA. So in a PFA universe, every coherent family is trivial. And we'll see the argument for both of these things. Sergey, do you think we should proceed like this, or maybe I should log in and log back out? I also wonder,
You can try to log out and log in, yes.
Okay,
or
yeah.
You can try to disconnect your phone.
Yeah, it's become, I don't know, probably 4 degrees cooler since I began speaking, I would say, and speaking, and maybe this affected the phone somehow. I don't know. We'll try, and then I'll come back and yeah. Thanks for your patience.
Илья, вы что-то говорите?
People may need to pin it again. It looks a little better.
Yeah, it's good now. It looks good.
Okay, I guess the phone just gets tired. Okay, and actually this might. Okay. Now, there's maybe one Yeah, okay. So I'll say, are there set theorists among you? There are some set theorists. So I mean, I could say I could do another page, or you could just talk to set theorists about what is a large cardinal. I could tell you what a large. I feel like. So we could jump into homology right now, the homology background, or I could say one more thing about set theory. I'll say one more thing about set theory, and then we'll jump into homology theory. Okay, so what I would say is the following. So I encourage people to think about the width of the universe. So you have the Girdle universe kind of narrow, and then you have a forcing axiom universe kind of wide. But we can also talk about the height of the universe. And all these universes that I was talking about, they have the ordinals, and you keep going up. But there's sense to this question. And one way of approaching this question is, as you look at omega, the first infinite cardinal, and you ask whether a property of omega happens again. You might be of a certain philosophical orientation that whatever happens should keep happening. And this is sort of one heuristic argument for large cardinals. So for example, if you have, so lambda equals omega has properties like this. 2 to the kappa is less than omega, or is less than lambda for all kappa less than lambda. This is very clear in the case of omega. This is just saying that the 2 to the n is finite for every finite n. And what I'll write as CF of lambda equals lambda. CF stands for cofinality. What this means is that the size, the minimal size of a cofinal set in lambda is lambda. Well, this is true in the case of omega. So if you have these two properties, and you are not omega, then you're called inaccessible. And this might seem like a very mild thing to ask, that what happens at omega happens again. But if you ask that this happens again, then when you look at your universe, at this lambda, this, everything below here, this, which we will call V sub lambda, is a model of Zfc. And you can kind of see, okay, one of the hard things as you go up, so you can cut your universe, but then there's a question of the power set, which might take you higher and things like this. But these are saying that these operations below lambda don't take you up. You stay below lambda. So V sub lambda is a model of Zfc. Now, by Girdle incompleteness, Zfc itself can't prove its consistency. So it can't prove that there's a model of Zfc. But if you have an inaccessible cardinal, then you have a model of Zfc. So just saying that there exists such a lambda is a stronger assertion, logically speaking, than just Zfc. Okay, so this is a fairly low large cardinal. And I'll give you another large cardinal, but this is sort of the idea of large cardinals. You can have these properties and they give you additional strength. And a number of natural assertions that arise within mathematics turn out to be maybe equivalent to one of these assertions or something, a large cardinal property. And again, that happens in these homology contexts. So I'll give you one more. So omega equals lambda. Yeah, so this, as I said, this has the properties that for any kappa less than lambda, any coloring C from lambda squared to kappa admits size lambda homogeneous set. Okay, so what I just wrote down here in the case of omega, this is Ramsey's theorem. So it's saying if you color the, so you just take the natural numbers, you color the pairs of the natural numbers in finitely many colors. Well, then you have an infinite set such that all the pairs from that infinite set get the same color. Okay, so if that happens again for some lambda above omega, then this is a weakly, this is what's called a weakly compact.
What is lambda bracket?
Yeah, this is a notation. So this is, yeah, lambda to the kappa is the set of x subset lambda such that the size of x equals
this.
kappa. Yeah, I'm sorry. So lambda to the kappa is the set of size kappa subsets of lambda. So lambda to the 2 is just the pairs in lambda. And I might use that again. So you can keep going like this, and actually, you know, I had someone's probably done it. People propose to get a tattoo of the following chart. But this is worth. So I talked about an inaccessible cardinal that's down here. Greater in strength is a weakly compact cardinal. And you can keep, and all of these at this point are pretty routine in set theoretic practice, up to a measurable or even a super compact. So you have these stronger and stronger large cardinal principles, each of which implies the consistency of lower things. And it's a fairly linear order. It's not quite a linear order. We think of it as a linear order, which is kind of amazing. So you have this linear order of consistency strength, of logical strength, but it's not quite, but it kind of is. And in some cases there are questions, and it might, so the relation between a strong cardinal and a super cardinal is a super compact cardinal is a big question set theory. But this is a very active area of investigation, is understanding these things and this chart. But Zfc is way down here at the bottom, and assuming a little more, assuming things like weakly compact already give us really interesting mathematics. And so this is another. So to conclude the set theoretic section, so you know, we have sort of the idea of Zfc is, okay, we're going to formalize mathematics, and then we have this scandal of independence, that when we formalize mathematics, well, we don't answer all the questions that we might want to. For example, the continuum hypothesis. How might we respond to that? Well, we could just take on another axiom. We could just say the continuum hypothesis is our axiom, but there are reasons not to do that. One of the reasons for this is that a model of PFA is in many ways more appealing for doing mathematical work than a model like V equals L. Another reason for this is that L, the model L, because it's so small, actually is incompatible with many of these large cardinals that I just pointed at. So the large cardinals can't live in L. Otherwise, I mean, otherwise it's very tempting to say, let's just take the minimal model, let's be happy. That's we're all going to agree on that. That's going to be our model of mathematics. But you would be shutting out a lot of these large cardinal principles. You would be shutting out the idea that principles of that properties of omega recur and things like this. So these are sorts of metamathematical, philosophical, and mathematical issues that remain unsettled. And that's kind of where things are at. This is the view from 30,000 feet or whatever. So with that, I think we can close out the set theory section, turn to the homology section. And again, please stop me if there are any questions. Okay. Now, again, I'm aware of speaking to a geometric topology. So okay, again, I think everyone knows a lot of things about homology here, and they probably know more than me. So, in part, maybe just to sort of give the camera a rest, I think I'll talk some of this out. I want to just give a little background as what I think of as really significant events, dates. 1952, we have Eilenberg, Steenrod, axioms. Okay. So again, please interrupt me, and please, if I'm saying anything stupid, please let me know. But a lot of the questions that I'm building to talking about have to do with axioms and the additivity axiom in particular. So the way I think about it is, when we learn algebraic topology, when we take our first algebraic topology course, maybe we use a book like Hatcher or something like this, and we take some basic spaces and we compute their simplicial homology, maybe their cellular homology, maybe their singular homology, and we see that we get the same result up to isomorphism. And in some ways, this is, as I understand it, recapitulating the historical development of the subject. And then a milestone in that development was the recognition that really what's going on here is a very short list of axioms, the Eilenberg-Steenrod axioms, which fully determine a homology theory on any simple space. So for CW finite. For finite polyhedra or finite simplicial complexes, finite CW complexes, we have the Eilenberg-Steenrod axioms. And again, we can give a picture of these axioms, which fully determine a homology theory. And these are things like this. You have the homotopy axiom, the exactness axiom, the excision axiom, things like this. And I think the next date I want to foreground is 1960, and this is Milner. So this is a very good book. It's Foundations of Algebraic Topology. This is Milner. I think the article is maybe on axiomatic homology. Maybe on.
Jeffrey, do you include the dimension axiom in Eilenberg-Steenrod axioms?
Are you asking if I do?
Yeah. Do you?
Yeah. Well, I believe that they do.
Okay.
But I'm not too particular about it. Really, I just want, if some of the screens in front of me want to include the dimension axiom and for this discussion and some don't, that's fine with me. Really what I want to motivate is just well, for what I'm saying, you want the dimension axiom to say, okay, there's a unique, we have determined a unique homology here, so we want that. But really all I want to do is motivate the additivity axiom. And I should also say something. There was a time, it's not recent, and I don't have a great medium-term memory, but there was a time that I was looking a lot at the literature from around here. And the references that I'm most familiar with, maybe for obvious reasons, are Milner's. But it's quite possible, and there are sort of signs and hints in the literature. I remember looking at it. It's quite possible that this was, the things I'm talking about were understood by then, maybe before then, within the Soviet Union. So in terms of, this is a sequence of papers, and I'm not making any strong assertions about priority or anything like that. But Milner, in this paper, extended the axiomatization of homology theories from finite CW complexes to infinite CW complexes, using one further axiom. And that's the following. So homology theory. H is additive. If, let's say it's additive on the class C of spaces, topological spaces. If for all x alpha alpha in A and C, and natural number P, the map the sum of the homology theories is the homology of the sum, is the idea. It's a very natural thing to ask. The map induced by, the inclusions x alpha into x alpha is an isomorphic. Okay. Is this clear and possibly familiar and correct, mathematically correct? So hopefully this is legible. This is the note that I write to myself. So singular homology satisfies these axioms. In other words, it satisfies the Islenberg-Steenrod axioms and additivity, but it has some drawbacks. And around the same time that Milner was talking about additivity, he was also noticing these drawbacks. So we could call this a Hawaiian earring. So if we look at the Hawaiian earring, I think we have to look at a Hawaiian earring where these spheres are of dimension 2 at least. But if we look at these, there's this paper, Milner and Barrett, looking at the homology of these, the singular homology of these with rational coefficients, observing that the homology groups are non-zero for arbitrarily high p, which is very unintuitive and maybe not a thing that you would want. So singular homology satisfies the axioms that we were talking about, but it also does some funny things. And this is also an opportunity for me to introduce this shape, which will be important for us. And I think of singular homology as reflecting sort of, so we have nice spaces, polyhedra or CW complexes, and we might want to move to a broader class of spaces. And we can think of several strategies for doing so. And I think of singular homology as reflecting one strategy. So that strategy is to approach complicated spaces in terms of simpler ones via maps of simpler spaces into X. So you have your simplices and they're mapped into X. This is the idea of singular homology. Another way of relating or approaching complicated spaces in terms of simpler ones is via systems of approximations. And systems of approximations might be you take an embedding of your space X into something like the Hilbert cube and you look at neighborhoods, or you might look at nerves. So these are the check approaches. Now, those neighborhoods, as they get closer and closer, so these neighborhoods, these might be nice open neighborhoods, so they might be polyhedra or homotopy equivalent to polyhedra, and things like this. But you get a system. And if we're talking about a system of neighborhoods, then this is our space, X, the one that we're talking about, embeds naturally into these neighborhoods. So with these two approaches, with these two ideas, you have, among other things, the arrows going in opposite directions. And there are advantages and disadvantages to each of these. This is the way I think about it. Again, I'm speaking to people who know more about it than me, but I think there are intuitive advantages to number two, but there are also computational disadvantages or complications that come with two. And these are related to the fact that this is an inverse system kind of setup. And so you're engaging with the inverse limit functor. And the inverse limit functor is a fairly complicated functor. And I think of, so everything that I'm talking about it's cued superficially by homology questions, but more fundamentally, it's about the inverse limit functor. It's about ways that the inverse limit functor really involves a lot of interesting infinitary combinatorics. Okay, so let me just recall. Let me just recall what the inverse limit functor is. Okay, now the handwriting's very bad, and I'll read this. While in many ways more intuitive, the second approach, the approach where you have a space and you have maps from that space, maybe into its approximations, this second approach can entail computational complications pertaining to the inverse limit. So what is the inverse limit? So I'm going to write an inverse system like this. An inverse system is always going to have objects. These objects might be topological spaces. They might be groups. It's going to have connecting maps. And it's going to have an indexing order, lambda. So I'll usually write it as a triple. And P alpha beta will take X sub beta to X alpha. And so if we have an inverse system, again, this could be an inverse system of topological spaces or groups, then we can take its limit. Now, sometimes this is written, with the backwards arrow. And one realization, so we could describe this categorically, but also more concretely as follows. So the limit is just the subset of the product where all the coordinates play well with the bonding maps. In other words, P alpha beta of X beta equals X alpha. Okay, so if all our spaces X of alpha, if these are all compact topological spaces, then it's not hard to see that this is a closed subset of a product of compact spaces, and therefore compact. So that's not hard to see. And so what complicates the inverse limit in algebraic settings is the fact that it is not exact. And that's the thing that I want to talk about. Okay, and again, to save time, I'm going to go ahead and I'm not going to copy out this drawing. I'm going to just give you an ugly drawing. So this is a standard example. When I say that the limit functor is not exact, here's one of the most basic examples of that phenomenon. So what I have here is a short exact sequence of inverse sequences of groups. This is an inverse sequence of just zeros. This is an inverse sequence of integers, in which the map from one term to the next one, or to the one below, is the ×2 map, all the way up. This is an inverse sequence. This is the same one here. And then over here, we have z mod 3z, z divided by 3z. And again, the map is the ×2 map. So we can look at this as it's a short exact sequence of inverse sequences in the sense that, okay, you have 0 going into z, and then you have the ×3 map taking z to z, and then you have the quotient. Okay, so this is a short exact sequence. But it's also an inverse system of short exact sequences, if you would prefer to look at it like this. And I'm going to write x for this one, y for this one, z for this one, 0 for this one. But if we take the limit of this short exact sequence of inverse sequences, what I mean is if we take the limit of each of these terms, and limit being a functor, we'll also take these maps down, then what we get is no longer exact. It's a map from 0 to 0. So the limit of this, again, it has to be a sequence of coordinates, of elements that play well with these maps. If the coordinate here is non-zero, then it has to be half of that number, but still an integer here, and half of that number, still an integer here, half of that number. You can see how you're going to run into a problem. So the only thing that's going to live in the inverse limit of this inverse system is just 0. So the inverse limit of this is 0. The inverse limit of this is 0. But when you're doing the ×2 maps over here, you're taking 1 to 2 and 2 to 1. And so the way I think of it is, okay, so the 0 comes down here, but you also have this sort of zigzagging. You have another zigzagging. You have 3 elements here. You have 3 sort of fibers. So in fact, you get something non-trivial here. You get z over 3z. So what you have is exact at this term and exact at this term, but is not exact here. It's not surjective here. And for this reason, we say that lim is left exact. Okay. And people have seen this. This is probably familiar.
I don't know, it depends.
Okay.
Some might have seen it, others not.
Okay, so what I want to emphasize is that you can have short exact sequences of inverse systems. You can take the limit and you can conserve that exactness on the left half of what you get. That exactness can fall apart at this last term. But actually, that's the beginning of a more interesting story. So if x to y to z is a short exact sequence of inverse systems, of abelian groups, then lim x to lim y to lim z 0. So we've seen that this is exact. We're exact here and here. But we might have a failure if we put a 0 here. But if we put something else here, namely lim 1 of x, and then lim 1 of y dot 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 dot. Well, not even dots. This is lim1 of y goes to lim1 of z to lim2 of z, x, and so on, is a long exact sequence. I'm not going to formally define these, at least not right now. And judging from the clock, probably not at all today. Lim by itself, we know what that is. And lim1, we're going to talk about that, but we're going to talk about that in a concrete example. For those in the know, these are the derived functors of the inverse limit. And they're given by taking an injective resolution of inverse system, and then you take the limit of that inverse system, and then you take the limit of that injective resolution, and then you take the cohomology. So these are the cohomology groups of that. And that gives you the derived functors here. But these are fascinating objects, and they've been at the core of my research for several years now. And to return to the homology story, again, to keep it in very broad strokes, and then we'll move to concrete mathematical arguments in about 7 or 8 minutes. Main point. And in all those references I was talking about, when I was talking about Eilenberg-Steenrod, when I was talking about Milner in 1960, they're talking about axioms, but they're also talking about the inverse limit. This plays a big role in Eilenberg-Steenrod's book. It also, lim1, one of the first places that it appears is in Milner's 1960 paper. And I think this is not an accident. In all these cases, people are thinking about homology theories on nice spaces, how to extend these theories to more general classes of spaces, and a natural approach to those generalizations is the inverse limit. But they're noticing a tension between the algebraic requirements of a homology theory and this idea of approximating a space by topological spaces. And that tension comes from the behavior of lim1. In other words, you can't hope for something like HP of lim a x alpha. You can't hope for something this nice in general. Kind of for the reasons that I was talking about. Kind of, again, I'm being very fuzzy about this, but kind of because of bad behaviors like this. In other words, you have algebraic requirements here that this is just not going to cooperate with. The lim functor is just not. Did someone have a comment? Question? You might be, Stanislav, you might be muted. If it was Stanislav.
Maybe that was just some occasional sound.
Okay. I got excited because I like questions. So we can't hope for something this nice, but the way I think about strong homology is okay, so this is still, I'm continuing my main point. This is still a main point. One may, however, balance the algebraic requirements of a homology theory with the project of systematically, let's say, just topologically approximating complicated spaces through a fuller maybe more sophisticated incorporation of the functors lim n into your homology theory. This, I think, is the idea of strong homology denoted H with a bar over it. Now, this, I think, is the idea of strong homology denoted H. Now, again, I know there are people on the line who know more about these things than me and who should feel very free to speak up if they have a different conception of what's happening here. Strong homology is a little complicated to define. A main reference for it is the following book, but it's not a small book. This is from the library. It's a thick book. To its credit, it goes through, it offers pretty much all the details. It's a very good book in this way. I learned a lot from that book, but I'm not going to bore you with those, not bore you, but busy you with those definitions. I'd also stress that there are a number of different ways of defining it than you see in that book. So strong homology is our focus in the following sense. So 1988, and this leads to our main problems, and things are going to start to connect as of now. So in 1988, Mardashich and Prosilov asked, is strong homology additive? Okay. Now this is a good question because a natural question. When I'm talking about strong homology as in some ways a very logical incarnation of this strategy of defining a homology theory through topological approximations. When I talk about strong homology in those terms, I should mention its many virtues. One of these virtues is that it satisfies all the Eilenberg-Steenrod axioms on any paracompact space, so on a very broad class of spaces, on paracompact pairs of spaces. It also satisfies the cluster axiom, which means that it's going to compute things like the Hawaiian earring in a kind of intuitive way. And so again, this was these were things that were being worked out at the same time that forcing axioms were being worked out in the mid-'80s. And I think once Martisic and Prosilov had understood these things, this was a very natural next question to ask. You satisfy all the Eilenberg-Steenrod axioms, and the thing that came after, historically, the Eilenberg-Steenrod axioms was the additivity axiom. So the question is strong homology additive? And on the class of CW spaces, just by the Eilenberg-Steenrod axioms, you're going to be additive. And also, you're going to be finitely additive. So where to look? At an infinite sum, you won't get a negative answer to this question with any finite sum. So you need to start checking infinite sums. And you won't get a negative to answer to this question with CW complexes. So you need to look at non-CW complexes. And so they looked at everyone's favorite non-CW complex. So I'm going to call this Y of D, which is, say, the one-point compactification of countably many d-dimensional disks. I'm sorry?
Open disks.
Open disks. Yeah. Good point. What if we put a circle there? So yeah, so Y sub D, you're thinking of contracting d-dimensional spheres. And the key computation well, again, just in the interest of
Sorry, Jeffrey, maybe you could also draw the picture for D equals 0, because it's very simple.
Yeah, I actually, amazingly, I had not thought about this until looking at your work. But yeah, this story doesn't begin at D equals 1. You can even go to D equals 0. And each of these kinds of sits inside, you know, as you go to higher D, then the lower D's sort of sit inside them. So this is what you're thinking, right? Okay, so you have just a sequence converging to a point.
Yeah, just one point computation of the countable discrete set.
Yeah, exactly. In fact, topologically, this is just omega plus 1. In other words, the natural numbers with a, you know, with a cherry on top, you know, somebody sitting on top. Okay. And Martisic and Prosilov computed the following. So they looked at these, and it's some work to compute strong homology. And they did that work, and they found the following. Okay. So over here, this is again so this is really what you would expect. This is what you would hope for. So P equals 0. This is telling you, okay, how many components do we have? We have 1. And then everywhere else, when you're not 0 D, nothing is happening. And then this is counting how many spheres do you have, according to the cluster axiom. Now, remember, additivity tells us that we would like we would like this to equal HP we would like this to be true. For P greater than D, we have no problem. We have a 0 and we have a 0. For P equals D, we have no problem. You can check, but in fact, those guys line up. But everywhere else, what this is asking is that lim k of A equals 0 for all k greater than 0. Now, I haven't told you what A is, and that's what I'll tell you next. But I want everyone just to take 10 seconds, look over here, compare what we have over here. This is countable disjoint union of things like this. You take the sum over here, you compare the homology of the sum over here, and you want equality in every degree, and this will only happen if your limits are vanishing. So, Martishich and Prosilov did this computation. They arrived to this recognition, and then they were faced really with this question. They wanted to know if this happens. When does this happen? How does this happen? And I'll tell you what A is. Omega C to the F of I and P F G A to G A sub F is restriction. In other words, we begin to see a familiar picture. You have omega, you have omega, you have omega squared. You might have F here, you might have G here. A sub F is the finitely supported functions from the space below the graph of G to the integers. I'm sorry, A sub G is this. A sub F is the same with respect to F. And then the map between these is maybe you have, maybe these, this is the support of G, well then you'll just look at this when you're looking at P sub FG of an element of A sub G. Okay, so this is A. And this may remind you of the picture which I drew before. It's not difficult to see that lim1 of A equals 0 if and only if every coherent family is trivial. And if I can find that, maybe we'll look at that page again. This is all I really want to say, I think, about homology. So this is, if people have questions, here we go. This would be a good question, time to ask them. So again, we had the question of the additivity of strong homology. That question was first examined, seriously examined, with a countable sum of Hawaiian earrings. And that led to this characterization, or this requirement. So strong homology will be additive. No, strong homology will not be additive if any of these lim n of a's is non-zero. And we have a very concrete characterization of lim 1 of a. Lim 1 of a, so remember, this is our main example. Lim 1 of a is 0 if and only if every coherent family is trivial. In fact, there's a natural group structure on the coherent families. You can add them pointwise. In other words, if I have a coherent family, a bunch of phi sub f's, and then I have another coherent family, a bunch of psi sub f's, then I can add them to get another coherent family whose f term is phi sub f plus psi sub f. So you have a natural group structure in our coherent families. And you have a subgroup, which is your trivial families. And in fact, lim 1 of A is isomorphic to the group of coherent families divided by the group of trivial families. So again, lim 1 of A is 0 if and only if every coherent family is trivial. And this is what we'll now focus on because this is sensitive to set theoretic hypotheses.
Jeffrey, can I draw a little picture to introduce some geometry into what you were saying?
Please
I'm
do.
afraid I cannot immediately explain the lim 1, but at least this system A, how to see it geometrically, okay?
Yes, please, yes.
So that should be very quick. Can you see my paper?
Yes.
So if we do the case, what was it, m or d equals 0, or p equals 0, I forgot. Then y 0 was just this countable discrete set compactified by 1 point, right? And we are taking the joint union of this from 1 to infinity. This y sub 0. So let me draw some picture of that. So we're just repeating the same picture infinitely many times. So maybe this is the first copy, this is the second copy. So we have this compactifying point here, and then this is the third copy, and so on. And now we can take the approximations of this set, or well, one way to take the approximation of this joint union is to take the identical approximations of every summand. And these approximations are obviously just by finite sets. So we can start from the 1-point set, then the 2-point set, the 3-point set, the 4-point set, and there are the bonding maps. So here it's there is just one map like that. So here we are collapsing 2 points into 1, and then these 2 points into 1, and so on. Here it just goes identically. Okay, so this convergent sequence is the inverse limit of this inverse sequence of finite sets. And we can do the same with this summand. So let me try to draw it quickly. Okay, so same maps here. And now, well, yeah, so you were talking about this strong homology, which is not quite the same as thinner technique of homology. But I think thinner is so let me explain the thinner technique of homology and of this space of this infinite disjoint union. Let me call it X, and you will see how this inverse system A appears, and then, well, that should already help a little bit because you just see geometrically. So we are going to take some compact. So okay, so here, well, yeah, we have. We can take some. So we have this set. This is X. This is our limit space, and let me call this T, the disjoint union of this just finite sets. Well, so it's infinite here, already infinite here. So okay, but each of these is finite. So now. Now, I think well, the thinner treatment of homology of this X is the direct limit of thinner homology groups of compact subsets. So we are going to look at compact subsets of X, and in order to understand them, we can look at subsets of this T which have compact closure in T union X. So there is an obvious way how we can add X as a compactification as well as an extension of T. So T union X has an obvious topology. And so possibility and another possibility is that we could take not this entire set but some subset here. So then something would be excluded here, something included. And so we are just looking at such subsets, and we call it S, and then the zero-dimensional homology of S homology, but locally finite. Basically, in this case, it's just homology with infinite support. So it's the product of copies of Z indexed by S. And that's all. Well, no. Okay, this is correct, but this doesn't give us a Mardashich-Praslov system. So the Mardashich-Praslov system is the sum, yes, of the sum of z to the power, so over all the sequences of z to the power.
Something like this, yeah, is the Mardashich. Yeah.
Z to the power ni. These are sequences. So you can see this z to the power ni in here. So this is, if you have ni elements here, then this is z to the power ni, the zero-dimensional homology, and then this sum. Yeah. So then there is this infinite sum. Okay. So we now have some compact set. It meets every such picture in some. So this is n1. This is n2. no, no, and alpha. Hey, I'm sorry. I think I cannot say it well.
No, I think this is.
I'm sorry about this.
No, I think it's helpful because I think in this setting, and it's similar with the, you know, if you have circles, if you have the one-dimensional, but in this setting, the way I think about it is, okay, can we see sort of?
Yeah, I'm trying to stop this. Yeah, okay, sorry.
I thought that was helpful. So you have, well, okay, so you have this infinite sequence of you have this infinite sequence of Hawaiian earrings, and strong homology is going to approach them via approximations, and these are going to be, as in Sergei's picture, these are going to be, these are only going to have, you know, these are only going to be finite parts of the Hawaiian earrings. They might be something like this, and then something like this, and then something like this. And these manifest, this is 2, this is 1, this is 3. These manifest as functions from omega to omega. These functions from omega to omega are sort of recording the approximations that we're using to approach the fullness of this sum. And if you, again, I think it is even clearer if you get the spheres and just look at the axes, and then it does look just like omega cross omega, as in Sergei's picture. This is a bit hand-wavy, but the point to believe, if not to fully perceive, is that beginning from this topological question or algebraic topological question, one arrives to this system, and from this system, you arrive to this combinatorial question. And there's a question for us about time and what to do now, in the sense that, Sergei, you mentioned that people might want to take a break at the very least at 2 hours. I thought of giving a few set theoretic arguments, but they would certainly take more than 10 minutes.
Sure, we can make a break.
Yeah. So
if
we could come back to
something quick that could also help. Yeah.
I think how about this, like in a movie, you know, like for the movies, I'll say, if so if you want to say goodbye now, then I thank you for your attention, but we'll take a break, and if you want to come back, then we'll do a couple set theory arguments that don't require a lot of background, and then I'll just, at the end of that, I'll review some of the results, and there's a lot of results. So these are questions about, can you get lim 2 and lim 1 of A equal to 0? This is a question from 2010. PFA does not do it for you. On the other hand, very recently, it was seen how to do this using the assumption of a weakly compact cardinal. This actually does have implications for the additivity of strong homology on the class of locally compact spaces. And there are descriptive set theory results that relate to all of this. You know, sometimes we have consistency results that have sort of a descriptive set theoretic interpretation. For example, when we're talking about the continuum hypothesis, every subset, this is the continuum hypothesis, every subset of the real numbers is either countable or of size continuum. Well, this is independent, as we saw, but it's true if we add the word open here. Every open subset of R is either countable or so, every closed or Borel or analytic. Well, here we will see that there's independence. This statement is independent of ZFC. Every coherent family is trivial. But if we add words like open or closed or Borel or analytic here, then in fact it's true. And recent work, which actually just posted on the archive today, extends this work to higher dimensions. Basically, for any it's non-analytic. So very recent work is probably what I would close by at least mentioning. But if any of this interests you, I'd be happy to see you again in, I don't know, 10, 15 minutes, something like this. And if it doesn't, I more than understand, and thank you for your attention already.
Very much, Jeffrey. So let's continue in 15 minutes, 7:10 by the Moscow time.
Okay. I guess we log out and come back in?
As you want, as you want.
Okay. Thanks again, and I'll see you soon.
Jeffrey, I'm sorry, I confused myself, but if you give me a couple of minutes, I will. I can correct myself. Jeffrey? Hi, Jeffrey, can you hear me?
I'm sorry, speak again, Sergey?
Yeah, can you hear me?
Yeah, I can hear you, but I will change the audio. So, 1 second. Okay, can you hear me now?
Yeah. Well, I'm sorry I took your time, but if you give me a couple of more minutes, I can correct myself.
Oh, sure, yeah. This is fine with me, yeah.
It should be quick. Sorry about my confusion. Yeah, but now. Can you see?
I see.
So I just confused this. So what is this Mardishich-Praslov system? So we have a function f from natural numbers to natural numbers from n to n, or you can say from omega to omega. And corresponding to that function, we have the following group. So it's a direct sum from 1 to infinity of direct sums from 0 to f of I. This is I, and this was f of copies of z. Okay, so how to see it geometrically? So we have our space X, this disjoint union, infinite disjoint union of copies of this convergent sequence. Now let us approximate it with nerves. You mentioned that the homology of X, H0 of X, is not equal to the inverse limit of H0 of the nerves, but we can anyway look at this inverse limit, or anyway this nerve. So how to see a nerve of this X? Well, we should just take some nerve of this converging sequence, some nerve of this converging sequence, and so on, and take their disjoint union. So for instance, we are taking this nerve here, and this nerve here, and maybe this nerve here, and then this nerve here. So this joint union is going to give us a nerve of X. And such a choice of a nerve here, and so on, gives us precisely a function from n to n, because so here we have 2 points, here we have 3 points, 3 points again, 4 points. So this is a sequence of natural numbers, 2, 3, 3, 4, and so on. It doesn't need to be strictly increasing, it could be any sequence. And now we are just looking at the zero-dimensional homology of this nerve. So the zero-dimensional homology of this 2 points is the direct sum of 2 copies of z. The zero-dimensional homology of these 3 points is the direct sum of 3 copies of z. And this is precisely the values of our function f. So f of this 2 is f of 1, this 3 is f of 2, and so on. Okay, so this sum here is just the homology of one of these finite nerves. And then we're taking the direct sum of all of them. And this is, I guess, by this additivity axiom for CW complexes. this is going to be the homology of this entire nerve. So this A sub f is nothing but the zero-dimensional homology of our nerve. And then, well, so we could look at limb or limb 1 or any limb P of this inverse system. Yeah, and I guess I should say about the bonding maps also. So if we have another such function from n to n, well, they could be incomparable, but if g is less or equal than f, then it means that every nerve corresponding to f is above or equal to the nerve corresponding to f. So this could be g and this could be f. And then we have this bonding maps here, which give us the bonding maps from AG to from AF to AG. And then that's it. This is how to see it geometrically. All right.
Thank you, Sergey. I think that's, yeah, thank you. I think that's very helpful. Do you think we should begin, Sergey?
Sorry? What did you say?
Can you hear me?
Yes.
Do you think we should begin?
Yes.
It's just us.
Sure, go ahead, please.
Okay. So just to recall, we have the main example here, which comes from the limb 1 of A, and we have the question of whether things that are coherent or trivial. And so first I want to give an example showing that CH implies no. CH implies that there exists a non-trivial coherent family, and therefore CH implies that strong homology is not additive. And Sergey, you have seen this. I'm sure you've read the Martishich and Prosilov paper. But this is a slightly different argument than the one that they give. So I guess there are fewer, because there are fewer people here now, we should feel freer to maybe talk to each other and say what we want to do and things like this, maybe. So if I speak of a kappa scale in omega to the omega, the picture that I have in mind so this is omega to the omega, but I'm going to draw one of them sort of tall or long. So maybe this is F alpha. F beta could be a little bit below F alpha for a finite length of time. Make F beta. And so on. And this is of height kappa. In the, well, actually, let's say strict ordering. Okay, so what I mean by a kappa scale is just a copy of this ordinal kappa in this, it's not a partial order because it's not anti-symmetric, but in this quasi order. So the quasi order, anytime I write like this, just like when I write equals star, that means two things are equal mod finite. Less than star means that f sub, when I write this, that means f sub alpha of I is less than f sub beta of I for all but finitely many i's. So it's the ordering of eventual dominance. That's another way people say it. And so a kappa scale is you have kappa many of these, and the ordering of kappa is the same as the ordering according to this. I think a very good exercise for people that are getting comfortable with set theory or infinitary combinatorics is the following lemma, that the continuum hypothesis implies that there exists an omega-1 scale. Why is this true? Well, you build this up by recursion. You start with some functions. You have your function 1, function 2. If you have function alpha, then you can just add 1 to every coordinate to get to your function alpha plus 1. The key point in building this up is that if I have anytime I have countably many functions, I can always find some g anytime I have a countable collection f, such that g is greater than star any f in here. How do I do this? If I have countably many functions here, then I can make the first coordinate of g bigger than the first coordinate of the first one of these. I can make the second coordinate of g bigger than the first coordinate of the first two of these. I can make the third coordinate and so on. So this allows us to keep going at any countable stage. I can keep building my scale at any countable stage. And the continuum hypothesis tells us that, well, in fact, I can keep going at any countable stage, and I can finish at stage omega 1. And if I'm careful also, then I can make sure that I've covered, so to speak, I've gotten above every other function. Okay, so we're not going to use CH. We're actually going to use a strictly weaker hypothesis, which is that there's an omega 1 scale. You could have an omega 1 scale and still have the continuum even larger. But we have this lemma. And now we have this theorem. If there exists such a scale, then there exists a non-trivial coherent family. And in consequence, lim1 of A is not 0. And in consequence, strong homology is not additive. Okay, so to prove the theorem, so we're going to recursively construct a non-trivial coherent family like this. Now, when I talked about non-trivial coherent families before, they were always indexed by omega to the omega. This is just sort of a skeleton of a non-trivial coherent family. We aren't using every function from omega to omega, but we're using a cofinal set. And because we define it on a cofinal set, it will be easy to extend it to something defined on all of omega to omega. Why is this the case? Because, well, if I have some function that isn't in this cofinal set, then there's somebody in the cofinal set above it. And then I can just define it to agree with that cofinal set above it. Now, the above that I'm talking about might be mod finite. There might be a little finite part that's cut off. But we don't have to worry about that. We can let all those coordinates be 0 because we're talking about coherence, which doesn't care about finite difference. So again, this is a kind of exercise. Anytime you have a non-trivial coherent family defined on a cofinal set, then it extends to a coherent family. Moreover, this coherent family must be non-trivial. Because if you had a trivialization, if you had a single function that agreed mod finite with each of these guys, then it would agree mod finite with each of these guys in particular, and this guy would not be non-trivial. Okay, so we're just going to build the skeleton of a non-trivial coherent family, and that will be enough. That's what I'm arguing. And the advantage of working on this skeleton is it's well ordered, so we can do things recursively. So we can go up. And that's what we'll do. So this is a very cute idea. And the first thing that you do is fix a bijection from omega squared to omega. And now suppose that we've defined our phi sub f all the way up to beta. Now, again, this is kind of an exercise, and if you don't believe me, you should interrupt me, but this is a countable collection of functions. It's a countable coherent family of functions because we haven't reached omega 1 yet. That's the idea. Anytime you have a countable coherent family of functions, it's trivial. Basically, by the same argument that I just gave, you can well order your countable collection of functions in order type omega, and then you can make sure to agree with the first one after a certain point, and then the second one after a certain point. So anytime you have a countable collection of functions, you can trivialize it. So let phi from omega squared to the integers trivialize it. And let phi sub beta, so now we need to define phi sub beta restricted to I of f beta minus. I'll say what that means in a second. This means below the graph of f beta equal phi restricted to I of f beta minus. So the picture here is here's f. This is what I'll call I of f minus. It's the space strictly below the graph. So we have I sub beta, which we need to define, and we have this trivialization, and we'll define I sub beta to be this trivialization below the graph of f, but that still leaves us the graph of f itself. Along which to define phi sub beta. Okay. And for all I and omega, let phi sub beta of I, f of I, some point here, I, f of I. Okay, so we want to define phi sub beta here, so this is f sub beta. Now we're going to use this bijection. And we're going to build this bijection into each of our functions along the way to sort of fight against or diagonalize against any trivialization of the family that we ultimately build. So it won't be clear right away while we do that, why we do this, but then it will. So when to define phi sub beta of I comma f sub I, I look at this point and I apply this bijection to it. Now this bijection takes omega squared and then it maps it to somewhere over here. It's taking omega squared and it's mapping it to omega. So here we have pi of I, f of I. And then we look up here and then we get f of it. And that's what our value for phi sub beta is going to be. The thing to check is that we don't run into any problems, that we've built a coherent family, we remain coherent. We haven't sort of stepped on our toes, but there's always enough room because we've made sure that our omega-1 scale, these guys, the graphs of the functions are off of each other after finitely many points. Which means that when I arrive to a new function, I'm free to define this graph however I like without getting into trouble with coherence. In short, the thing to check is that we can do this. And I claim that we can while staying coherent. If so, then that's the construction. Now I just need to convince you that the function that we build is non-trivial. And that will conclude the proof.
Jeffrey,
Yes.
why? So, if you just define this phi sub beta like you defined it below the graph, what if you define it also on the graph? What goes wrong?
Well, I want to use the graph. Nothing goes wrong in terms of constructing the coherent family. But I might end up with a family that's coherent and trivial at the end. So what I suggest, Sergey, is let me show you that this family is non-trivial, and then we can come back to your question. So I claim that this family is non-trivial. And the proof is, suppose for a contradiction that psi from omega squared to z So this is our trivialization. So we suppose for contradiction that for psi from omega squared to z, psi restricted to I of f sub alpha equals star phi sub alpha for alpha less than omega 1. Now fix alpha less than omega 1 with f alpha greater than or equal to star psi compose pi inverse. So remember, pi is a function from omega squared to omega. So pi inverse will take omega to omega squared, and then psi will take that to the integers. But that's a function from omega to the integers and from omega to the natural numbers in particular. And it's a property of our scale that for any function from omega to the natural numbers, or basically omega to the omega, there's some function above it. So now we go find such a function, and that gives us our alpha. This is what we'll use for a contradiction. For all but finitely many I less than omega, phi alpha of I comma f alpha of I equals psi of I of f alpha of I. Why is this true? This is true just because psi trivializes this collection of functions. So we know that for all but finitely many arguments, this has to equal this. And this, well, this is just kind of doing nothing. And now you start to see why we made the definitions as we did. So psi of this is, of course, psi composed with this together with its inverse. But this guy here, this guy here, we know is less, let's make it greater than. This guy here, for all but finitely many I, this guy here is less than f sub alpha of what's happening here. So now we can put f alpha in place of this. Of pi of I, f alpha of I, and this equals phi alpha of I, f alpha of I. And now look at these two that we have here. For all but finitely many I less than omega, this is less than this. This is a contradiction. And so to come back to your question, the way I think about this proof is we build a coherent family using the fact, so a natural question is, where did we use omega 1? A place that we used omega 1 is that at every step, we could find a trivialization. And we could find a trivialization because we so far had only a countable coherent family. And a countable coherent family is always trivial. This argument would break down if we were trying to go to omega 2, because we might get stuck. We might have built a non-trivial coherent family by accident before we got to omega 2. So we're able to continue all the way up to omega 1 and able to sort of cover omega squared. And that's good. And that's our coherent family. But we need to do something more to be sure that what we've built is non-trivial. And what the scale does is it sort of pulls the graphs far enough apart that we can build things in there that sort of fight against or diagonalize against any potential trivialization. So if we have a trivialization, then again we can go and we can find an f alpha that's high enough that then we can get this contradiction. It's kind of a cute argument. And it's due to Alan Dow and Simon and Gervon. So there was the Martishich-Praslov paper, I think it was 1988. And immediately after, there was a paper, maybe a few months after, by these three authors. Martishich-Praslov paper showed that they saw that the continuum hypothesis implies that there is a non-trivial coherent family. This paper by Dow, Simon, and Vaughan is where this argument first appears, and it's from a strictly weaker hypothesis, which is just that the cofinality of the continuum is omega 1. In other words, that you have a omega 1 scale. And if you're interested, then we'll do the open coloring axiom, and then we can talk about the final results. So the open coloring axiom, I think it's a really beautiful, principle. And it's the following. So the open coloring axiom, and this is due to Todorcevich in the 80s, late 80s. So it's the following assertion. So you take any separable metric space X. And again, so these are just unordered pairs. When I write bracket X2, these are unordered pairs from a separable metric space into two, it's just a partition into two sets. So we take these pairs and we partition them into two sets. And we ask that one of them should be open in X squared in the collection of pairs. Now you have to think a little bit about what is the topology here? What does it mean to be open? Because I'm asking for unordered pairs. If I was asking for ordered pairs, it would be clear enough. But I think it's clear enough, and I'm not going to belabor that unless you want me to. So
then you said that you are removing the diagonal from the product and then taking the quotient by the factor exchanging involution.
Yeah.
Okay.
Or you could look at it as, a subset of X squared cross X squared. It's the same thing. XY, comma, WZ, such that X equals Z, Y equals W, X not equals Z, Y. In other words, if X is separable and metric, then this is separable and metric. And then you're looking at these guys such that you have, I want to say XY comma Y comma X. And so this is, I don't know, probably a closed, that satisfy these, and it's probably a closed subspace of this. And so it has its metric. And I'm sure it's equivalent to what you just said, or I would. So we take the unordered pairs and we partition them into two collections. Sometimes this is called the open graph axiom. We think of K0 as a graph. Or sometimes if we're looking at graphs, then it's this is a natural axiom to bring in. So I think there's sort of two pictures that we should have in our heads. K0 should be open in X squared. Well, if we think of X squared, we're thinking of maybe, so like you said, here's X cross X, here's the diagonal, maybe we throw that away, and we can think of, really we're just working on one half of the X cross X. And so K0 is open just means that we're looking at an open subset over here. But also we're talking about graphs. So if I have an X here, I have a Y here, and I have an edge between them, then you think, okay, well, there's actually an open neighborhood of X, an open neighborhood of Y, such there are edges between all those points also. Now, the open coloring axiom says that in any situation like this, either of two things happens. Basically, either K0 is very big or K0 is very small. K0 can be big, meaning that there's a complete graph. So just like this is, this is the complete graph on 4 vertices. This is saying that there's a complete graph on uncountably many vertices within K0. This is one possibility. So possibility 1, you have a complete uncountable graph. Possibility 2 is basically saying that you can color K0 in countably many colors such that no 2 vertices, no 2 neighboring vertices have the same color, which is saying that it's small. Small in this may be very large, uncountable setting, so it's countably chromatic, we might say. More formally, it's saying that, okay, we can take our separable metric space X, and it's a union of countably many sets, such that each of these lies in K1. So I should say this is a partition, this is a disjoint. So each of these, the pairs all lie in K1, which means they don't lie in K0. Okay, so none of these edges fall within the graph. So again, these xn can be thought of as countably many colors for the graph K0. This is the open coloring axiom. So the key facts are that the proper forcing axiom implies the open coloring axiom. The proper forcing axiom is very complicated to state. You have to know something about forcing, but the open coloring axiom, I didn't say anything about forcing at all. And it's something that I do, the idea is it can be applied more generally. It's just a mathematical principle. Now, the other thing that it implies is that in the previous argument, we use the fact that any countable subset of omega to omega has a bound. OCA implies something stronger, which is that any size aleph 1 subset has a bound. So I can have aleph 1 many functions now, and I can find a G which is above them. In particular, this implies that the continuum is not of size aleph 1, because then I could find another function above it. So OCA implies that the continuum is bigger than aleph 1 already. And more importantly for us, OCA implies that every coherent family is trivial. Okay, and then the argument I think just takes 2 pages maybe. And it's a really typical application of OCA. So we fix a coherent family. And then we're going to use this coherent family to define a metric on omega to omega and an open graph. And then we're going to use OCA to conclude that the family is trivial. Okay, so what is our metric? Anytime I have 2 distinct functions, f and g, then I'm going to say delta of f and g is it's the first place where they disagree, or it's the first x coordinate for which phi sub f and phi sub g disagree. So here's phi f, phi g. Well, this is g, but this is phi g. First place where they disagree, this is I, j, and then this is delta f, g. And then this defines a metric. If I take 1 over 2 to the delta of fg. And it's easy to check that with this metric, and it's a natural metric. It's saying that the farther to the right f and g are alike, the closer they are, the more they agree. So that's the metric, and it's easy to see that omega to the omega with this metric is second countable, and therefore separable, because the basic open sets are just take anybody here and functions to the integers, and then anybody that, so that sort of gives you a basic open set. So this is a separable metric space, and now we can define our K0. This is going to be our graph. And then we'll apply the open coloring axiom to this graph. So this is just the disagreement graph. So the pairs here are those F and G, such that phi sub F of I comma j does not equal phi sub G of I comma j for some I and j. First thing to check is that this graph, in fact, is open. So if I have some F and G in here, then they disagree on a certain coordinate. So phi and G, so if F and G disagree, and they disagree on this coordinate, then I know that if I take, so to speak, the ball around F of radius 2 to the minus I, everybody in that ball has to agree with F on this first out to I, on this first portion of phi sub F. So everybody in here is going to look like F on this first part, and everybody in here is going to look like G on this first part, and therefore they also are going to disagree at the same place. And therefore F prime and G prime are also going to fall in K0, which means basically that we found an open neighborhood of F comma G. For any FG in this graph, we found an open neighborhood which also falls in this graph. So it's an open graph. That's the kind of argument. Sergey, does this make sense? Do you believe me?
I'm still at the definition of K0. So why? So it is saying that phi sub F is not equal to phi sub G for some pair ij. So that means phi sub F and phi sub G are just different functions.
Ah, I'm sorry. That's a very good point. I'm sorry, this is sloppy. This is for some I in their common domain. So I could have, so Sergey, I'll say this with my hands. So I think this hand is phi sub F. And then I have phi sub G, which might be, G might be strictly above F. It's possible that on the intersection of their domains, they have exactly the same values. In that case, they won't be in K0. K0 is the disagreement graph. It takes those pairs, exactly those pairs where when we look at their common domain, there's some disagreement. And then the claim is that the disagreement graph, this graph, is open. And the idea of the claim is, okay, if I have two guys and they disagree here, then I have an open neighborhood of F that will also have that value. And I have an open neighborhood of F such that everybody in that neighborhood, every phi in that neighborhood would also have that value. And I have an open neighborhood of G such that every associated phi in that neighborhood would also have that value. So everybody in these neighborhoods, they're going to have the same values as F and G, and therefore they will also have the same disagreements. So they will also fall in that graph. This is the idea of the claim. So if it's an open graph, then we can apply the open coloring axiom. And the open coloring axiom gives us two options. Now, in the first option, there's a complete uncountable graph. So there's an uncountable y such that every pair of elements in y is in this graph. What that means is that there's an uncountable collection of f's and g's such that every pair of them disagree in this way. Okay. Now, if there's an uncountable one, it could be size aleph2, it could be size aleph3, but certainly we can just take a subcollection of size aleph1. So without loss of generality, there exists, we can just assume that y is of size aleph1. And because of what I said, OCA implies we can find a bound for y. We can find somebody who sits above everybody in y. Now we're going to use this G to get a contradiction. So we have this G, and we have all these functions in y. And for every f in y, G is above f after some k. The graph of G is above the graph of f after some k, but because there are uncountably many elements of y, there is some k such that there are uncountably many elements of y, such that G is above, I'm not saying this well. What I'm saying is there exists a y0 and a k such that G is above the functions in y0 after k for every one of these functions. And y0 is uncountable. And this is just a pigeonhole principle. In other words, if I say that G is, so if G is a bound for y, for every element of y, then I know that if I take a function in y, then G is above that function f after some, maybe after 1. And G is above another function in f, maybe after 2. And G is above another function in f in y, maybe after 7. But there are uncountably many of these functions, and they're going into these countably many holes. So uncountably many of them have to go into a single hole. That's what K is. So it's a pigeonhole argument, and that's what we do again. So now assume that, so we can thin Y down while remaining uncountable. And we can say that everybody in Y is below G after K, to the east of K. Okay, and then we can look at the initial part of these functions. And this is, each one of them will look like this. And each one of them will, so let's say that K is 5. And we look at the value of F0, F1, F of 2, F of 3. So that'll give you something here. What I want to emphasize is that this gives you a finite region. It gives you whatever F of 0 is, plus whatever F of 1 is, whatever F of 2 is, F of 3, F of 4. That's everything. Those are all the coordinates in play here for F. And then you have the collection of functions from this finite region to the integers, and that's a countable set. And you have finitely many finite regions here. So again, we have countably many things, countably many possibilities for P sub F restricted to I of F intersect K times omega. So there are countably many possibilities for what this can be. So again, we can thin down our y0 to a y1 for which this is constant, for which these all look the same by the same pigeonhole principle. And then again, now we know that everybody here, so everybody in Y1 is a function f that begins like this. So they can't disagree with each other here in this initial part. In other words, the distance between them. So for all f and f prime in Y1, delta of f prime is greater than or equal to k. We definitely know this now. Now look at each of them, and each of them is going to disagree with G someplace. So here's some F, and it's strictly below G. So we're going to have some disagreement here, disagreement here. But again, we have only countably many possibilities. So we're looking at the space below the graph of G, and then we're looking at finite subsets of that space. Well, there are only countably many finite subsets. And then for each of these finitely many subsets, we're looking at their functions from them to the integers, and there are only countably many such functions. So there are only countably many possibilities for the ways that phi sub f can disagree with phi sub g. And so again, we can thin down to a y sub 2 such that for all f and y sub 2, and y sub 2 is uncountable still, for all f and y sub 2, the phi sub f's disagree with phi sub g in exactly the same way. But what does this mean? This means that they can only agree with each other. Okay, so this is our contradiction. This implies that these are not in K0. We found that they agree with each other. We've actually found an uncountable set of them that agree with each other. And so it's not possible that we can have a complete graph on an uncountable. We can have a complete subgraph of K0 on some uncountable set. We got a contradiction. That uncountable set, we could use that uncountable set and we could play it against countable things again and again and again until we got down to something uncountable that just agreed too much. And this means that we're in the second situation, and this completes the proof. So now OCA tells us that there exists an X sub n. There exists a countable collection of X sub n's whose union is omega to the omega. Such that the pairs all fall outside the graph, all fall in K1. Okay. So OCA says if we don't have one, and we showed we don't have one, then we have this situation. And my claim is that one of these X sub n's, which is a collection of functions from omega to omega, one of these must be cofinal in omega to omega. Now, if this claim is true, I'll prove this claim, but if this claim is true, then you take that one such that the functions are cofinal. These are f in x sub k, and we know that x sub k is cofinal, and we know that these guys, because the pairs do not lie in k sub 0, we know that they agree with each other. And because they agree with each other, we can take their union. And because it's star cofinal, anytime I take some other function, one of these guys in x sub k is above it, and therefore I know that anytime I take some other function g, then I know that phi sub g restricted to I of f equals star phi sub f restricted to I of f g. And what that tells us is that this union that we took or any extension. So it's possible that when we take x sub k and we take the f's in it, that maybe there's some piece that they don't quite catch, but it's basically finite. This union, if we extend it to a function from omega squared to z, it will trivialize phi because it's made up of these coherent functions that completely agree. So the idea is we find this co-final guy, and then we take the union, and then this gives us a trivialization. And the last thing that I'll say, and this will close out the arguments. Why is this co-final? Suppose that it's not co-final. Or suppose that none of these is co-final. If none of these is co-final, then what that means is for each n, there exists an f of n, f sub n, with no g in x of n, such that f sub n is dominated by g. Okay, but this is a countable collection. And because it's a countable collection, we can take somebody that dominates it. But this function has to live somewhere, because we have the union of x sub n equaling. So it has to live in one of these x sub n's. But if it lives in x sub n, then we get a contradiction, because we know that h dominates f sub n. And the whole definition of f sub n is that it's not dominated by any element of x sub n. Okay, so this shows the claim. And together we have OCA implying, altogether we have OCA implying that every coherent family is trivial. And in other words, that lim1 of A equals 0. So, Sergey, it's just you and me. And we can stop anytime that you want.
As long as you're not tired, I'm very interested to continue.
No, I'm not too tired. I'll just tell you about, thank you very much for your interest, and thank you again for the invitation. I'll tell you about how I think about what's happened since, and so everything that I described is just, those were consistency results for lim1 of A. And these questions about coherence and triviality, they were stimulating to set theorists, and there were maybe 5 papers in set theory thinking about, okay, how do these relate to set theoretic assumptions, coherence and triviality? That was the mid-80s and mid-90s. And I think people had said, they had done a lot with coherent families and with lim1 of A, and sort of the question sort of settled down. But of course, the additivity question, if we look at the Martashich and Proslov paper, was not just a question about lim1 of A. It was a question about lim(n) of A for any positive lim. And so this was my advisor, Justin Moore. And I actually have with me, this was, it's in a coffee shop one day, like these are a list of questions that he feels people should be looking at. He was trying to get me to look at these questions, and this became my thesis work. I didn't answer, I think, any of them then, but in the time since, they've been answered with co-authors. But I think he was so to be honest, I think set theorists, they probably looked at lim2 of A and it looked just too complicated, too algebraic. It didn't look like the kinds of things that they were comfortable with, and they left it alone. But Justin really pointed at this question, and he insisted on this question. And one of the reasons that he did, I think, has to do with the following theorem. You might know this theorem. So basically, this is due to Goblet, I think, 1967. In order to have non-trivial lim n of A, or non-trivial inverse systems more generally, you need the indexing set to have big cofinality. You need the indexing set to be big. Okay, so some of the things that set theorists are interested in are omega-1 and omega-2. And so one of the reasons that this question is interesting is to get lim1 of A. So when the continuum is Aleph1, then lim1 of A is non-zero. So to get lim1 of A to equal 0, you need a bigger continuum. So you need the continuum to be at least Aleph2. Is it true that when the continuum is Aleph2, then lim2 of A is non-zero? That's true when so in other words, the sort of secret question here is, let's say 2 to the Aleph naught equals Aleph n. Does this imply lim n of A is non-zero? This is true when n equals 1. I think many of us suspect that it might be true, or something like this might be true for all positive n. And a reason that set theorists care about this is because set theorists really, I think when I'm talking about this timeline, set theorists have come to understand omega-1 or Aleph1 pretty well. And it feels like the next frontier of research, the next thing for us to understand is Aleph2. And so lim2 is very good at sort of posing questions about Aleph2 and sort of testing our understanding of Aleph2. The other thing is, okay, so to get additivity, we would like all the limits to vanish. We know that's the least thing. We need all the limits of lim A to vanish. And because of this theorem, to use it in sort of the other direction, it tells us that if we can have a small continuum, then we don't have to worry about the higher limits. In other words, if we had this plus 2 to the Aleph naught equals Aleph2, then we would be very happy because this tells us that lim3 of A equals 0, lim4 of A equals 0. We don't have to worry about the bigger limits. So I guess the last thing that's stimulating about this question is that, okay, with co-enforcing, we can add lots and lots of reals, we have lots of ways of making the continuum very big. But really, models of set theory that we understand, that we're really able to work with, the continuum is almost always Aleph1 or Aleph2. So this question was really pushing on all these things. He was asking it so that either we have to understand if this is true for n equals 2, or we have to find models in which this is not true. We have to have a large continuum and a lot of control on the model at the same time. And so I think it was a really good question. And the first place that any set theorist would think to look is in a PFA model, because like I said, PFA is where we think things go well. So you don't have so for example, PFA implies OCA. So PFA implies every coherent family is trivial. PFA, we think, usually tells us that we can put local things together nicely. So I think one hope in 2010 was that there is an axiom that gives us lim1 of A vanishing, And maybe it also gives us lim2 of A vanishing. And since PFA also implies this, it would give us everything vanishing. And this would be an interesting result, because it would tell us that the PFA model is kind of a nice model, maybe for things like homology. It would be a nice world for homology. You have an additive, strong homology. But it turns out, and this was my first result, that PFA implies that lim2 is non-zero. And in fact, since PFA implies OCA and OCA implies that lim1 equals 0, then we have a complete picture of the vanishing of the limits under PFA. So a lot of the other questions, so this made things look harder. I mean, the goal was always to get the limits to simultaneously vanish. And this was the baby version of that question. And so Chris Lambie-Hansen is a very skilled set theorist. He and I started talking, and he had a lot of ideas. And after about a year of this, we were able to do this. So we needed a large cardinal assumption, a weakly compact cardinal. And then basically we forced to add that many reals, a particular kind of real number. So we added a lot of reals, and we used a very strong cardinal. But at the end of it, we had that the simultaneous vanishing of all these guys. But there were a lot of questions that were left over from this. One of the questions was whether we need the continuum to be so large, whether this result might be compatible with something more familiar, a continuum closer to the Earth. This was one question. And the other question is whether we really needed a large cardinal. And then after a lot more work together with Michael Hirschek, we were able to get rid of the large cardinal. We were able to get this down to, so you have aleph 1, aleph 2, aleph 3, dot, 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 dot. Then you have aleph omega, and then you have aleph omega plus 1. So the first possibility after all the aleph ends, we were able to get it there. And I would say in this direction, the big question for set theorists is whether it's consistent that lim n of A equals 0 for n greater than 0, and 2 to the aleph naught is less than aleph omega. I would say this is probably the biggest remaining sort of combinatorial question coming out of this. And so this is, and also, maybe all of this would be meaningless, but Velichkovich and Vignati in 2021 also showed that there are models in which the limits are non-vanishing for arbitrarily large n. Again, you need to make the continuum large to get this, but this happens.
There are some nice axioms which implies this vanishing in the second theorem and non-vanishing in the third theorem, or you just prove consistency directly?
That's a very good question. No, these are very complicated forcing axioms. I mean, forcing arguments. There's not really an axiom where we can say this. And that's also true here. I mean, to a set theorist, this might be meaningful, but it's not really. So I would say weak time and something like this. So you can write it down like this. There's sort of a short list. For them, there's a short list of requirements, or a short list of ingredients, but it's still not totally transparent for a set theorist. And probably even less for a non-set theorist. So that's kind of the bad news. But there is kind of some good news in that direction that I'll say. That will be the last thing that I have to say. That's the most recent work. So the idea, though, always with lim n of A. So this is a very good combinatorial question for set theorists, but really the original question was, can we get strong homology to be additive on some nice class of spaces? So as you know, there's a limit. So the original Martischitz-Proslov paper was 1988, and what they had was the consistency result. So I think their paper is called "Strong Homology is Not Additive," but probably the more accurate title is "It is consistent that strong homology is not additive." It's true that strong homology is not additive, that's a Zfc theorem, but that wasn't really known, I think, until 1995. And Proslov showed that. But his example it's a fairly far out example. There's a lot of room between his example and some of the spaces that we might care about. So there was still some room for hope. And in 2020, with my advisor and an undergraduate at that time, Nathaniel Bannister, we showed that in that model with the weakly compact cardinal. So in this model here, the first model where we got all the limits to vanish, as suspected, if you can sort of deal with this combinatorially, then you can deal with all the limits that might give you problems from a certain class of spaces. And so in that model, strong homology is additive, and it has compact supports on the class of locally compact separable metric spaces. And as we discussed on email, we thought this is probably, I don't know how much better we can do. But one reason we don't know how much better we can do is because, or we didn't think we could do much better, is because of this Lisicka example. I'm not sure if I'm saying his name right, but that's an example that I've looked at and I've gotten kind of annoyed at because I don't have an intuition for what it's doing. But it's a non-locally compact separable metric space that claims to be a counterexample to additivity. I think claims to be a counterexample to compact supports. Now I'm confused. I think it claims to be a counterexample to compact supports. But these might even be the same thing in this context. If that example isn't perfectly correct, then it's possible that this could still be pushed a little more.
I'm not saying that I found an error, but when I tried to understand it, I somehow didn't understand.
Me too. I think it's probably worth looking at more, looking at harder. If you ever understand it, please let me know.
Let you know if I have any progress about that.
Okay, and so those are further results on additivity. And then the last thing is descriptive set theory, kind of. Which I don't know how people think about it in Moscow, but I was most excited to talk because I think of these things as sort of coming from people like Luzin and Suslin.
Before the break, one of the members in the audience was Vladimir Konovey. Maybe you have heard of him.
Yeah, yeah, he's a very impressive descriptive set theorist, sure.
Yeah, he's no longer with us now.
Yeah, he's a very strong mathematician in this area, and yeah, widely respected in this area. I have his book checked out from the library back behind me.
He also wrote an somewhat elementary book for, I don't know, for undergraduates about the axiom of determinacy.
Oh, really?
I think it might be only in Russian. I'm not sure if it has been translated.
It might be, because I've never seen this.
Well, it doesn't contain any new results. It's just some summary, I think, of some simple things known about axiom of determinacy. And I liked it very much when I was undergraduate.
So, just to ask, so set theory was part of your undergraduate or even high school education?
Well, not much of set theory. Not really. I really took some course, more serious course in logic when I was in graduate school. But yeah, I was not so serious about it. I was more into topology.
Yeah. Yeah, I don't think people really. I mean, I didn't encounter it. I didn't get into it until graduate school, certainly. But I think you mentioned in the email that in high school you liked it.
Yeah, well, that was a special high school, not an average high school, definitely.
Yeah, but still, I was excited at the idea that people are seeing set theory in high school.
A little bit, yeah, a little bit.
So these last results are descriptive set theory results, and I wouldn't call myself a descriptive set theorist. I'm an aspiring descriptive set theorist. I think it's really beautiful math, but I feel very amateur at it. So I think because it's late, you're going to have to believe me or not believe me. But if you take the set of functions that look like this, they admit a natural Polish topology. If I say Polish space, does that?
Yeah, sure, but actually it's interesting. So you have defined some separable metric topology on some other space, right? In a previous proof.
Yeah, and actually, that probably would, something like that would work. You could just say, okay, well, if I have these functions, then again, I look at the first place where they differ, and this gives me a metric. And or, you know, a common trick is, okay, so we're looking at functions. We're looking at partial functions from omega squared to the integers. And so we're looking at elements of I think this would work. So this is a countable set, and a function is a subset of this. So a function is an element of the power set of this. And power sets of countable sets admit natural Polish topologies. Why is this? Because You can encode the, so if I have a countable set X, and I look at the power set of X, well, there's a natural correspondence between this and 2 to the X. What is the correspondence? It's just a characteristic function. And so possibly by rearranging things, I can look at the power set of X as, and since X is countable, 2 to the omega. So I can always take a power set and I can look at it as a polar space. I can look at it as a Cantor space. I can identify it with it. And then I can sort of pull back the topology to the power set. Now, that doesn't tell me that this is Polish, this collection of, so what this is this is a subspace of this. It's a subcollection of this. So it's the functions that meet certain requirements. There's a graph of a function, and then they're below the graph of that function, and then. But the point is that these requirements are fairly easy to write down and fairly easy to check. And when they're fairly easy to write down and fairly easy to check, the way a descriptive set theorist will think about it is that means they're probably something like a closed or a G delta subspace of the polar space. And that's enough to know that they're Polish. So that's sort of the lazy way that sometimes descriptive set theorists think about things like this. They say, okay, well, there's a power set somewhere, and then I know that this is a nice subspace. Okay, and if I say analytic set, which I think of as Suslin's discovery, or a sigma 1,1 set. So this is in an uncountable polar space, such as this, the analytic sets properly contain the Borel sets. What are the analytic sets? They're maybe the projections of Borel sets or images of polar spaces, but they're more complicated than Borel sets, but they're not crazy yet. They're still kind of manageable. And so, as I was mentioning before the break, many consistency results have descriptive set theoretic analogs. And so, not this. So we have this kind of thing. So every subset of the reals is either countable or size continuum. This is one statement of the continuum hypothesis. This is true for open sets. Every open subset of the reals is either a countable or size continuum. It's true for the closed, for the Borel, for the analytic sets. And so there was also this result, which is closely related to the OCA argument, that every open or closed or Borel or analytic coherent family is trivial. And in fact, Todorcevich has a really pretty theorem that looks like this. A non-trivial coherent family. So this is that polar space I mentioned. So the polar space of functions from below a graph to the integers. So this polar space. So a non-trivial coherent family is a collection of points, and it's a subset of that space. You know, it's a phi sub f and a phi sub g. It's a collection of points in this space. So it's a subset of this space. So if I have a non-trivial coherent family, then in fact, not only is it non-analytic, so it can't be analytic. So it has to be a sort of complicated set. But it's a really interesting kind of non-analytic family. It's a non-analytic family whose intersection with any compact set is very simple. It's a countable union of closed sets. So again, one of the ways that I think about coherent families of functions is they locally they get along. Locally they agree. There's a question of whether you can globalize this agreement. this is like a topological kind of, so locally, so if you take a non-trivial coherent family and you just look at it as a subset, a set of points, locally, in other words, in the eyes of any compact set, this is a very nice set. But globally, it's something very complicated. So again, there's this sort of tension between local and global that they give us. And this is like a different face of that tension. That's why I like this theorem. Well, non-trivial coherent families, well, they correspond to lim 1 of A. So any witness to lim 1 of A is non-analytic. And this is, I think, this is late 90s to Dorchevich. And yeah, the most recent work is the following. So properly interpreted, so this other pretty stuff, we didn't get into that too much, but it's true that any witness to higher lim n of A is also non-analytic. And the way this connects to your question is, I can send you a copy, or you can just find it on archive. I think it came out today. But some of it's very hard, really set theoretic arguments, but there's one thing that we thought could be useful outside of set theory, and that was, we just isolated, there's a basic principle, and it's called the partition hypothesis. And I think just because I'm tired, I'm not going to try and state it. But the partition hypothesis is just it's a statement about colorings. And it says that when this statement about colorings is true, then derived limits of, I'll just say, many inverse systems that are indexed by omega to the omega vanish. So this is a single principle that really sort of lies at the core of several of these arguments that I'm pointing at here. We just sort of cooked it down to a single principle that you can sort of say, okay, if I have this principle, then I know some derived limits vanish. And definitely A vanishes. We showed that A vanishes anytime you have this principle.
Which other derived limits vanish?
Well, I think it's true. Yeah. So how did we prove this? How did we prove this? Well, the combinatorics is basically the same as we used to get, I mean, basically the same as we saw with A. But we had to look at the Mardashich-Prasilov systems, the systems that correspond to these guys. Now you can still associate to these guys you know, so what we want here is, so I'm going to say I have G, I, J. And I have, again, natural numbers, natural numbers. So in the case of the Mardashich-Prasilov system, I think of it as you have Z squared here on every column, Z cubed, Z, z squared, z cubed, like this. And you have a function, and that function is picking out guys from each of these columns, and then it's giving you these projections. You still, so I don't know what would happen if we got so sort of carefree with systems that are indexed by omega to omega, and we allowed for weird maps. It's important that in the inverse systems that we're talking about, there's this sort of vertical organization where you still have along each column really an inverse sequence. And then these omega to omegas running across them. Okay, so this class of inverse systems in which you have an inverse sequence in the columns, and each of these is a finitely generated group, which could probably be weakened, maybe with more assumptions or not. But this class of systems corresponds to this class of spaces in the sense that if you can get the limits to vanish for these guys, then you have additivity for this class of spaces. And so the partition hypothesis applies not only to A, but to things, this generalization of A. And I think that's all I have to say today.
Very interesting. Thank you very much.
I appreciate very much your invitation, and again, these are busy times. These are complicated times, obviously. I myself will be moving in a month and a half, but I was really impressed with what I saw on the archive, and I look forward to getting to know your work better, and I hope we stay in touch.
I'm sorry I made a confusing remark, which could frighten off some members of the audience.
No, I thought it was helpful.
Yeah, and maybe what you said today could help me to fix the problem with my theorem, which you mentioned. The two assumptions are contradictory, which I thought could be non-contradictory. Yeah, so I'll think.
Their intention, I think they're contradictory, although that should be checked. Yeah, let me know. I mean, let's stay in touch.
I need to think about it, but the problem, I'm now doing some other things, and then I'll have to do something, some third topic soon. So it's difficult for me to find time to focus on it.
Yeah, this is.
I hope eventually, maybe in the summer, I can think about it more.
I understand. Good luck.
Thank you.
And again, thank you again, and be well.
All right. So thank you. Goodbye.
Bye-bye.